Welcome to the Advanced Software Architecture course. My name is Michel Chaudron, and this is the lecture Quantitative Analysis of Software Architecture. We focus on part 3, the performance engineering process. This slide shows a performance engineering process. On the slide, I will briefly mention all the steps. In the next slides, we will explain these steps in more detail. 1. The first step is to establish the performance objectives of the system. The next step is to identify threats for achieving the performance objectives. Next, we identify which use cases are most critical to the performance of the system. And 4, based on the use cases, we create performance scenarios. This involves estimating how often each of the use cases happens. And 5th, we measure or estimate the resource requirements for each use case. And based on the preceding steps, we are able to build a workload model. In addition to that, we must, based on the architecture design, estimate the capacity of the resources that our system offers. This forms a capacity model. And by combining the workload model and the capacity model, we can build a performance model. Analyzing the performance model will then tell us whether the current architecture design does or does not meet its quality objectives. Ideally, this analysis also tells us where in the systems are the bottlenecks. These are the places where we may need to change the design. In this slide, we want you to practice with estimating workloads. Here are a few example questions. How many requests does the university library system receive per hour? How many requests does a bank receive per hour for processing transactions? Or consider an airline booking system. How many requests does it receive for checking availability of seats on flights? These are difficult questions to answer, but the architect needs to answer them, and in doing so, he needs to come up with realistic estimates. This slide explains the performance engineering process. In the light blue balloons, you can see where the information for performing each step comes from. The architect needs to get information from stakeholders, from deployment engineers, and many other stakeholders as well, and combine this with his model of the system architecture. Next, we will go over the steps in a bit more detail. Performance is critical to the success of today's software systems. However, many software products fail to meet their performance objectives when they are initially constructed. In determining performance objectives, one needs to call up on the creativity of imagining various aspects of the use of the system. What performance would make the system attractive? Or what performance would make it unacceptable? How do we expect that the load on the system will grow, for example, when the number of users grows, or when some key technology changes? The utility of systems may differ depending on how much too late their response comes. This is illustrated by the 2 questions at the bottom of this slide. For hard real-time systems, a late response is considered useless. For example, an automated braking system in a car. And you can see that the value of the response drops down from some value to 0. For soft real-time systems, a late response may be annoying, but not dramatic. You can look in the graph and see that the value drops a bit steep, but it doesn't go to 0 directly. There's a sloping off. Here one can think of delayed rendering of an image in the video calling system. Ideally, we express these performance objectives through quantitative criteria. Such objectives may be expressed in terms of response time, throughput, and workload. This slide lists some heuristics for thinking of risk scenarios for performance. This is the second step in the performance process. One can start thinking top-down or more bottom-up. Top-down approach would be by start thinking about assumptions on the environment, how realistic they are, or one can look into boundary cases or extreme cases. And another good way of thinking of complicated situations is by thinking of combinations or event or mode changes. More bottom-up risks for performance, they come typically from the solution and the technology. One can look at the number of interrupts or caching and how it affects performance, or dynamic memory allocations. In the third step of the performance engineering process, we try to identify critical use cases. The critical use cases are those that are important to the operation of the system or that are important to the responsiveness as seen by the user and other stakeholders. In the UML, use cases are represented by use case diagrams, which you can see on this slide. The selection of critical use cases is also risk-driven. So we look for use cases where there is a risk that, if performance goals are not met, the system will fail or be unattractive. Typically, the critical use cases are only a subset of the use cases in the system. In this example, we indicate risk of use case with a shade of yellow. In the fourth step of the performance engineering process, we look at identifying performance scenarios. For each critical use case identified in the previous step, we next need to identify key scenarios. That means activity patterns of a use case across the system. And we focus on scenarios that are executed frequently or are especially critical to the performance of the system. Together with these scenarios, we have to look at the number of instances of these scenarios that may happen concurrently and hence have a shared load on the system. We represent scenarios by a combination of sequence diagrams. Again, you can see how we reuse the diagrams that we made in a performance analysis. In the example, we elaborate the use cases register, search, and pay items in cart by means of sequence diagrams. Next, we move from a use case perspective to a systems perspective. We do this by estimating how many sequences of which type happen simultaneously. In our example, we may consider as a worst case scenario that 1,000 search actions may happen simultaneously with 100 pay actions in 1 second. Step 5 consists of determining software resource requirements. The processing steps during the execution can be described in terms of resources that they use. This we call resource claims. A resource claim captures the computational needs that some action of the execution requires. For example, we might specify the number of database accesses required in an execution step. We would then need to have some characterization of the load of a database access. This may also be characterized by a probabilistic distribution. Resource claim information can be associated with the definition of operations in the class diagram, or it may be attached to specific sequence diagrams. When done early in the development process, these may be simple best or worst case estimates. And later, as development progresses and class design is elaborated, the estimate may become more precise. As an architect, you need to find out which software and hardware resources are important to take into account in your model. For example, for some systems, caching may be relevant, while for others it is not. The main categories of hardware resources are network capacity, compute capacity, and storage capacity. This slide illustrates that we can use the sequence diagram as a basis for estimating workload from a software perspective. The messages that are exchanged between classes A and B, see the red balloons in the diagram, imply communication actions. The size or volume of the messages needs to be summed together, and together forms the load on the communication resource. A box on a lifeline indicates a compute task for that object. In this slide, the green balloon on the lifeline of class B indicates such a task. We need to estimate the computation resources that this task requires. It may be estimated in terms of CPU cycles or database accesses. We obtain a system-level picture of the computational workload by aggregating all the resource claims of all computation tasks in the sequence diagrams. Analogously, we can obtain a system-level view of the communication load by aggregating all communications from the sequence diagrams. The aggregation is illustrated by the red lines. They lead into a workload model. From the capacity perspective, we need to aggregate all the computation resources and also the communication resources. These can be inferred from deployment diagrams. This aggregation is suggested by the green lines. Finally, the resource claims and resource capacity together feed into a performance model. An analysis of this performance model then gives insights into key performance indicators, which includes response times, waiting times, and utilization figures. Step 6. Designing the hardware infrastructure. The capacity perspective is computed on the basis of a deployment model. This deployment model includes a description of the hardware infrastructure, which states the following: which hardware or computing nodes are used in the system, how are hardware nodes connected through network components, and which software components are mapped, that means which are running on which hardware nodes. For the capacity perspective, we assemble all the computation resources and also the communication resources. Next, the resource claims and resource capacity together feed into a performance model. An analysis of this performance model then gives insights into key performance indicators such as response times, waiting times, and utilization figures. This slide aims to globally illustrate how all of the information comes together in a performance analysis of an entire system. In this slide, we show how we combine the following: use case diagrams. These are annotated with a frequency indication, how often they are executed, and this can, for instance, be estimated based on the number of users. Then there are sequence diagrams. These indicate the execution pattern of actions and messages between components. Remember that these messages have been annotated with resource claims, and the actions in sequence diagrams have been annotated with compute claims. Then there's a deployment diagram. This diagram shows where in the system which components are executing. And now from this diagram, we can deduce between which physical nodes in the deployment model messages will travel and on which node computations will be performed. Actions from sequence diagrams are translated into a load on a particular hardware node, and messages from sequence diagrams are translated into a load on the network. Please note that one component may be involved in multiple sequence diagrams. Also, different components may be running on one hardware node, and this implies that they share this resource. Therefore, their load must be combined. Multiple actions and messages may be happening at the same time, concurrently, and because of this, loads from different components or messages must also be combined. There are actually different ways of combining loads, but the different ways of doing this are beyond the scope of our course. For those of you that want a more in-depth view into quantitative theories for performance analysis, we recommend to start by looking into queuing theory. This slide mentions a few classical texts on this topic. Summary of this performance analysis. We recommend you use performance analysis methods to support architectural decision making. For performance, you could use queuing networks. There's actually lots of tools around that support this. The slides we have shown, the example methods, show that some of the analyses are really back of the envelope. You can achieve lots of value by doing a little bit of calculation, even if your model is not perfect, which they never are. So the bottom line is, if you haven't analyzed it, don't build it. This is the lecture Quantitative Analysis of Software Architecture Part 3. It is now finished. Thanks for watching.